So with this, now let us go to, with this background, now let us go to guided diffusion for conditional generation. So let's say this is guided diffusion. Guided diffusion models for conditional generation. So all the commercially available tools that you see today are used as conditional generators. Why? Because given a particular text, let's say that you say that I would like to generate the picture of let's say an animal playing some game. Okay. Now the diffusion model would do that. So now it is not simply sampling from the data distribution, but it is sampling from the conditional data distribution. Okay. So now the question is, how do you modify diffusion models to be able to sample from the conditional distributions? So let's say that for this to happen, the data that we should have tuples of this sort. It should have tuples like x0 comma y, okay, where y is the conditional variable, conditioning variable. So this can be, so the example can be the following, right? Example can be x0 is let's say that it is an image. So we are building diffusion models for images. Let's say y can be a class label, a discrete class label, where let's say that you have a data set that has hundreds of classes. So what you need to do is you want to generate an image of a cat or a dog or a house or whatever, right? Which is denoted by variable y, or this y can be some text embedding. So the more practical example where you are given a particular sentence and you need to generate data from that particular sentence, one can generate an embedding which is a vectorized version of a given natural language text and use that as the conditioning variable. Now given a natural language text or a sentence, how does one convert that into a vector called embedding? There's something that we will see later in the course when we look at transformers. But yeah, assume that y is a vector. It can either be a one-hot vector which contains ones and zeros, which represents a particular class label, or this y can be a real valued vector that represents the embedding given corresponding to a particular text. In this example, it can be anything. So basically I'm saying the data that we should have in this case has to be the pairs, okay, the tuples of sort x0 comma y, where we have the image, or rather the data from which we need to sample, and y is the conditioning variable. This is the kind of data that we need. Pairs, basically pairs of images and text. If you want to generate image or pairs of images with the class labels, pairs of images with the corresponding textual descriptions, if you want to generate class conditional data. Okay, so now the goal is to sample from the conditional distribution which is p of x0 given y. Okay. So now, so far we have been sampling from the marginal distribution p of x0, right, using diffusion models. Now we need to sample from the conditional distribution. The question is, how do we modify the question? How to modify a DDPM to sample from the conditional distribution. Sample from the conditional distribution. Okay, so we will see two ways to do this. So one is what is called as the classifier guided conditioning, and the other thing is classifier free conditioning. So let us look at both of them. So this is, first thing is classifier guidance, classifier guided diffusion. Okay, how do we do this? So recall that DDPMs are score predictors. So we will use this formulation of DDPMs being the score predictors to do this. So that's why I said, right, the reason we looked at multiple interpretations of DDPM is that one of the interpretations are becomes handy in different use cases, where in the case of converting DDPMs into conditional samplers of conditional distributions, score based interpretation is much handy. So recall that DDPMs are score predictors. Okay, score predictors. Now from a conditional distribution perspective, from a conditional distribution, or rather from a conditional sampling, let me write it fully in the previous case. Score predictors predicting the true score of the marginal distribution, predicting or regressing the true score of the unconditional or the marginal distribution. Marginal distribution, which is represented as gradient of log of P of x t, and this is xt. So this is what we saw, right? I mean, we saw that the DDPMs are nothing but predictors of the score of the distribution of the noisy sample xt. Now if you want to change this to a conditional sampling perspective, from a conditional sampling perspective, the goal is to predict or regress over the conditional score. Right? So now if we want to sample from the conditional distribution, what do we have to do? We just have to ensure that the prediction or the neural network that we are building has to sample from the conditional score given by gradient of log of P of xt given y. So at every noise step xt, we need to sample from the conditional score. Okay, or rather we have to estimate or predict the conditional score. So now how do we do this? So let's write that. So we have the conditional score defined as P of xt given y, and this is with respect to xt. Simply use the Bayes law here. This is the gradient of log of, what is the definition of the conditional distribution? We have that to be equal to the marginal times the posterior divided by the prior, right? So this is simply Bayes law. Okay, so this is equal to the gradient of log of P of xt with respect to xt. Then we have plus the gradient of log of P of x t, other p of y given xt, y given xt, this is with respect to xt, and we have the third term which is the gradient of log of py with respect to xt. Now this term goes away, this is 0, right? There is no dependence on xt to this term. Great. So now what did we do? We just wrote down the conditional score that we want to estimate. The conditional score now, log of p of xt given y with respect to xt is now equal to the unconditional score plus the derivative of log of p of y given xt, which is the posterior with respect to xt. This is a very important result. Now recall that, so this is the result that we will be using now. What did we do? We just represented the conditional score that we would want to estimate, okay, while doing the conditional generation. As the sum of the unconditional score and another gradient term of log of p of y given xt with respect to xt. So now how do we modify? So this first term is the unconditional score, the second term is, let's call this the classifier gradient. Note that this is not score of any sort, right? Because the score is defined as the log of the likelihood with respect to the random variable upon which the distribution is defined. So this is p of y given xt, so it's a distribution over y, and the gradient is with respect to xt. So therefore it cannot be called a score. So we call that classifier gradient. Okay. Now we'll have to just implement this in our DDPM, right, to be able to sample from the conditional score. Now how do we do that? So let us get back to our score estimator. We have the score estimator. Now because it's a conditional sampler, so we just have to give y also as an additional input here while we are predicting. Okay. Now at the output it is of course predicting the score, or we can say that it is predicting the noise, because both of them are equivalent, as we know, right? So this is epsilon theta, this is what it is predicting. It's also predicting the unconditional score. So what is this? This is for predicting the unconditional score. We know that predicting noise is equivalent to predicting unconditional score. This is predict unconditional score. Okay, this is predicting the unconditional score. What about the second term that we have? So for that, what is to be done is you train a classifier separately. So this classifier, what does it do? This takes xt as an input. So this is a classifier, okay, and predicts p of y given xt. So this can be either a classifier or a regressor. Okay, why can it be a regressor? Suppose y, which is the conditioning variable, happens to be a one-hot vector, then you can use a classifier. Suppose it happens to be an embedding vector, then this becomes a regressor network. So what does this do? This classifier or regressor. So now this classifier or regressor is trained separately, okay, a priori. So it is trained separately than the unit. So what does it do? It takes to predict predict y, which is either the class label or the embedding, class label or embedding from xt. So what is done is, recall that while we are training this unit, right, if you recall how we train this unit, we sample t different time step randomly and give it as an input to this to predict this. Whenever we take a noisy version of the input data, we also pass it through the classifier and train it separately. Okay, so if you train it separately, then this becomes a predictor for p of y given xt. Okay. Then what is done is, for during training the DDPM, what we do is that we take xt and do a forward pass. So this, let's say that this is a trained classifier, we train it separately. So let me call it pre-trained. Okay, now pre-trained, what I do is, during training the this particular unit which predicts the noise, so we give xt as an input to this. This is one forward pass, okay, and compute the output of this. So this is computing epsilon theta cap, which is equivalent to computing the unconditional score. We saw that, right? Epsilon theta is equivalent to predicting the unconditional score. Okay, that is what we saw. We also compute the conditional score by passing xt through this classifier. Okay, first you pass this through the pre-trained classifier and get p of y given xt. This is forward pass, and through the reverse pass, just do a backward pass through this pre-trained classifier. What do you get? You take the gradient of log of the output of this neural network, okay, and you do it with respect to xt. Now, as one can find the gradients of a particular loss function with respect to the parameters of the network, one can also find the gradients of a neural network with respect to the input as well. So because you can treat this input as well as another vector, so you are simply finding out the gradient of this with respect to the input vector. So now this gives you the classifier gradient. Okay, now when we are doing a backward pass through the unit that we are training, what we should do is that we should take the gradient of the loss with respect to theta of this particular term, which is the unconditional score, and we also add the gradients of, we will say, simply add this gradient as well. So we'll take this and just add these gradients that we have computed. Okay, so now this is what is this doing? You just add these two gradients while you are doing the backward pass through the unit that is trained. So classifier is separately trained beforehand, beforehand than training the unit. Okay, it is trained, and you compute this particular gradient, add that gradient, and do a back propagation. That's all. So this is how one would use a classifier or a regressor to guide the DDPM to be able to sample from the conditional distribution. Now there is one other question that I assume that it is obvious, but I'll nevertheless state. So in all these interpretations, training is okay. When we are regressing over one, we can look at regression over different kinds of parameters. Now, does the inference change is the question? Okay, so once you have trained, how do you do inference? So we saw that inference in DDPM is simply sampling through the decoding distribution p theta of xt minus 1 given xt, right? That is what we saw. And how do we do that? We simply do it via this particular equation where xt minus 1, when we need to sample from the normal distribution having the mean mu theta star, where theta star represents the trained parameters, and the variance is known. So this mu theta star, we just have to sample from a normal distribution and just scale it with the fixed variance, and add it with the mean that is being predicted by the neural network. So every time we pass the previous xt through the neural network that is already trained, get your mu theta and then compute xt minus 1, and we do it iteratively, right? Now in all the other interpretations, right, suppose you have built your neural network as a regressor over epsilon instead of mu theta, then you should just use the reparameterization that relates mu theta to epsilon. So where is that? So we did a reparameterization here where mu theta was related to epsilon, right? So now instead of, you just replace this mu theta, the expression of mu theta here, mu theta in the inference equation that I wrote, using this, that's all. Okay, so now the output of this neural network will be epsilon theta star cap, okay, because the way we have trained our neural network is as that of regressing this particular quantity. If that is the case, then in the inference equation we just have to replace mu theta star with this particular equation where epsilon theta cap of xt is coming from the neural network. That's it. So nothing changes in the as far as the inference procedure is concerned, right? So here this mu theta star is simply replaced by whatever reparameterization that we did for mu theta star. That's it. Okay, so nothing has changed. Okay, so now coming back to the conditional generation case, again the same thing happens, the exact same reparameterizations. Now instead of using the reparameterization of the conditional score, we just use the unconditional score in the definition of mu theta. Where is it? So let's get back to that. I'll just show you that quickly. Now here, yeah, mu theta is represented in terms of unconditional score here. Instead of unconditional score, you just write it as the conditional score log of p of xt given y, right? So that's it. So during inference, you just take the output of the neural network, and the neural network also will have y as an input. And please note that this classifier will not be used during inference at all. So this is only used during training to so-called guide the diffusion process using the conditioning variable. Now once this is trained, you just discard this, and whatever output this neural network is giving can be seen as the conditional score, and use the usual inference procedure to do a conditional sampling. So that is about doing conditional sampling. Okay. Now the problem with this formulation is that the quality of this entire procedure depends upon how good this classifier is, right? Because if the classifier is not trained properly, then you don't get this gradient properly, and if you don't get this gradient, then you are not estimating the conditional score in a proper way. Now the quality of this entire procedure depends upon the quality of the classifier here, and training this classifier is not that easy, because look what you are expecting this classifier to do. Suppose xt correspond to the noisy version of, let's say, a cat image, then irrespective of the noise levels here, like at all noise levels, okay, you are expecting the classifier to predict the class as cat. Now it's a very difficult task to do, because the more the noise that is added to x0, the more difficult for this classifier to predict the underlying class. So now what happens is, in the above procedure, training the classifier at different noise levels is difficult. Therefore, there was another method that was proposed, which is called classifier-free guidance, where the sampling from the conditional distribution is accomplished without having the dependence on the classifier. This is called classifier-free guidance, okay, where the idea is that we wrote the score using the Bayes law. We wrote down the conditional score, right, as a sum of the unconditional score p of xt plus the score, or rather not the score, the classifier gradient, right? This is what we wrote. Now one can again use the Bayes law and write this particular term, which is the classifier term, in terms of xt given y minus, this is simply rearranging the terms using the Bayes law, right? This can be written. So now if I plug in this equation in the above expression, so how did I get this? This is simply the Bayes law. Please refer to previous equations that we derived. So just rearranging these terms, okay? What we are doing is expressing this term in terms of the difference between these two terms, that's all, okay, and plugging that back into this equation. If we do this, then we'll end up getting nothing. We just get, say that LHS is RHS. Instead of that, what people do is that write down the conditional score that we want to represent in terms of the unconditional score. The unconditional score remains as it is. You just add a constant, okay, some lambda times this thing. So we had p of y given xt here. So you see that you have p of y given xt. Now we'll replace p of y given xt using this particular equation. But if I do that, I'll simply end up getting nothing. So I'll just add a constant, a scalable constant, okay, that controls how much of the conditional score and unconditional score I'm using. Okay, I'll just put a lambda here. So please note that this is not exactly equal. This becomes an approximation now. Okay, and classifier free guidance is rather an approximate method because these are not exactly equal. So only when lambda equal to 1 this becomes equal. In that case, we'll go back to classifier guidance. Okay, so if we do that and then rearrange the term, so this will be equal to some lambda times p of xt given y plus 1 minus lambda times, this is simply rearranging the terms, the score log of p of xt. That's it. So this is the score. So now whatever we need, the LHS, which is the conditional score that we would want to estimate, xt given y that we would want to estimate, now is represented as a convex combination of, so here lambda is a hyperparameter. So this is the key equation in classifier free guidance. So what did we do? We just represented the conditional score in terms of unconditional score and conditional score with a constant. So lambda is a hyperparameter, experimentally tuned hyperparameter. So this is more of an empirical way to deal with the problem. So how did we do that? So now whatever we wanted to estimate is now given as a linear combination of unconditional score and conditional score. So here we got rid of the problematic term of p of x comma yt. So there is no need for a classifier here. So how is it done? The way it is done in practice is as follows. Okay, we take this usual regressor. Okay, and we have y that is as an input. Once if you give y as an input, you can interpret this as regressor over the conditional score. You can just say that this is regressing over the conditional score log of p of x t given y. Okay, then you need a regressor over unconditional score as well. So to do that, what is done is, in practice, you just make another copy of this same neural network, okay, and give y as a null text or a null label or a null text. Suppose you are doing text conditional thing, right? You can make it all 0. You can give it as the embedding corresponding to a null text. Okay. So now this, what does it do? This is a regressor over the unconditional score, because the conditioning that you have is null, right? You can actually look into this as a regressor over the unconditional score. So now what you do is it's simply making another copy. Okay, this is of the above. So basically what we are doing is, given a particular pair of image and text, we take the image, add the noise, give y as an input to this unit and regress over the unconditional score, and you take the same xt and condition it on the null text and regress over the unconditional score. Okay, and then add the gradients of both, add both the conditional and unconditional scores before the gradient step. That's it. Of course, with lambda scaling, you need to scale it with lambda and 1 minus lambda. Okay, you just add the conditional score, or rather I'll write it this way. Add both the lambda times conditional score and 1 minus lambda times the unconditional score. Before the gradient step. So now this, why is this important? This is important because we are representing the conditional score in terms of lambda times the conditional score and 1 minus lambda times the unconditional score. We just take a copy of these two, do the exact same thing, but the only thing that is done is once we give y as an input, the embedding of the text or the class label as an input, the other time we give the null text or null label as an input, which is all zeros or the embedding corresponding to the null text, and give it as an input, compute a regress over both of them and add the gradients and back propagate through the same neural network. There aren't two neural networks here. It's the same neural network that one takes an input of y and one takes an input of the null text, and you add them and back propagate once using the gradient of both. Okay, and as I said, the sampling does not change at all. During the sampling, you will have to give yt as an input at every xt. Right? That is why you are sampling. That is how you are sampling from the conditional model or conditional score, and the rest of the sampling remains exactly the same. Okay, so this is how this is actually the state of the art for all these models that you see these days, right? I mean, where you give a text and models like GPT etc. generates an image corresponding to that text. These are the models that I are using, and this is the state of the art which is being used right now, which is classifier-free guidance. Okay, with that we come to the end of discussions on DDPM. The next set of discussions will be on another class of models called DDIMs, which are denoising diffusion implicit models, that has several advantages over DDPM, which we will discuss next. Thank you.